Okay, so the first thing we're going to do is, where did we have it? We had the famous theorems. Let's remove all the ones that just could produce errors here.
Do we know the source of those errors?
Yeah, it's just that these are not theorems that are done by they're not in the Metamath database.
Oh, then we should remove them. Yes.
Yeah.
Yeah.
Right. And
You should just generate a fresh graph. It's just an outdated database, I think.
really, I don't think it's that outdated.
Well, we scrapped that list from the Metamath site itself. It only included the theorems that they proved there. So
Well, you mean the famous theorems, or you mean the Metamath graph altogether?
the famous theorems. It's not 100, right? It's just those that Metamath database contain. It's just
Yeah, I
the
know,
more
except
recent one. So it shouldn't be any missing there.
no, these are. Oh, well, okay, but look, for now, let's just get rid of these. Okay, so let's just say, it just doesn't matter. I mean, we're not, yes, there are a few missing. So what? I mean, none of these are particularly.
Well, you never know. It could be the deepest one or the shallowest one or something is amongst this
It could
batch.
be, but I'm
So
not.
you don't want to throw away information unless it's very
Oh,
costly to get
how
it.
do we get a new Metamath graph? I don't think it's easy to do. We can go back and try and correct this later, but let's for now just go through.
Okay.
And
Fine.
okay, so here.
Oh yeah. Oh yeah. Right.
Okay, so let's go through. Maybe we should make yet another. Okay, so here are famous theorems. And now let's say we just copy over the stuff from the top here. This is different because we wanted to have okay. Okay, so let's do select in here for vertex out component of Metamath graph, comma, last of hash, length of that, let's say, is greater than 2. $60. Okay, how many was this? Okay, so 13 went missing. Okay, this is fine to have 60 theorems here. Okay, so now let's go through, and what we were doing here was for each theorem, let's just generate this again. We were trying to get Okay, what are we getting here? So we're getting the, okay, so these are total theorems on which it depends, followed by, well, total sources, maybe we can say there. Then the next one is total distinct axioms. Then the next one is total distinct definitions, right? Okay, so now what we want to do is we find here this is now for each one it's is that just axioms? Yes.
Yeah.
Axiom depths. Okay. So then we want to take all the axioms that are here. So let's take the axioms. Now we can find the axioms because we've got that association which characterizes things by field. Okay.
Yes.
So that was Metamath domains. I think. Metamath a sock. Let's just take oh, look at that. Okay. Okay. All right. And then we've got another mapping that we must have somewhere else that maps these domains. Okay, so let's say -5 just to see what it has there. Okay, fine. All right, so this is by domain. So what we can do now is Metamath a sock. So let's take the axioms. Where do we have the axioms? I think we had the axioms computed somewhere else. Oh, let's see. The axioms are otherwise known as, oh, actually, yeah, that's the definition. So that's what we want is axiom a sock. AX.
Yeah.
Okay, fine. Now we want to look at those. Okay. So let's just say keys of that. And then we want to do that for Metamath a sock. So we want to index into Metamath a sock. Of hash arrow that. Okay. So that's our okay, so this is now giving us a sense of what the actual axioms are. So we should cut out, well, we'll have to see whether those supplementary axioms show up. Okay, but this is a good ordering of axioms because this will be by category, right?
Okay.
And so now let's do the following. So let's say of these, we want to make a picture. The axiom dependencies are here. And so what we want to do is okay, let's do this. So let's say this is the ordering of axioms, and then we'll subsequently decide on the color coding and all that kind of thing. Okay, so then it's kind of interesting, actually. I mean, this is oh wow, missing key absent. Well, we'll have to deal with that later.
Yeah, there are quite a few like that.
Well, what is interesting to me here is that the number of sort of genuine axioms. I mean, we've got ZFC here.
Yeah, it's modest in size.
It's really
It's-
modest. I mean, it's
yes.
basically, and let's just see how many of those famous theorems depend on anything other than the modest size.
Yeah, right. Wow, 56.
Well, it's interesting to see these real and complex numbers. You know, first of all, it's interesting that there are number axioms here as well. That must be Peano arithmetic. No, real and complex numbers. That's not Peano arithmetic. Where is Peano arithmetic?
There's no
Maybe-
piano. It's a separate database, right?
Oh, this is set theory. Okay,
Should we get the axioms from the other databases?
we should, but this is okay. So this is not mentioning. Is this the axioms? Yes. Okay, so let's go ahead here and, well, keys of axiom are sock. We can just use that as the index. Okay, so let's go ahead and do the following. So let's say axiom depths. Say first of axiom depths. Okay, so here, this will basically be turned into position in keys of axiom sock of hash sub 1 1. Okay, so this is now well, it's basically hash 1 arrow hash 2 of this, and that is axiom depths. The hell is that? Oh, position. Oh, no, I see the problem. This is hash map that over hash 2. Okay, there we go. Okay, so those are the, so what we want to do now, these are going to be the labels of the lines, right? Those are the labels. What we're now going to do is similar to what we did with the ticks thing before, of this is, so for each of these, it's an array plot. Okay, we can say normal of sparse array. Actually, let's do this. We can do this here. Normal sparse array of this thing, arrow 1. Oops. Position of that the hell? What's that? Okay, let's look at length of keys of axiom of sock 120. Why does it think there are that many elements? Oh, I see the problem. I see the problem. Silly, silly me. Okay, hold on.
Holding.
There it is.
Okay.
I think that will be fine. Okay. Okay. So now we want to say, so let's say, okay, with u equals this, array plot of last slash at u, and then we want to say frame ticks arrow. How did I do that in that previous case? For axiom systems in the wild. Okay, let me just copy this. This was my frame tick specification. Okay, so I don't care about that. That's the thing across the, well, I will care about that actually. That will be the list of axiom names, which we might as well put in there. Keys of axiom of sock. And then this here is first slash at u. Then this should say mesh arrow true. And let's see what happens. Oh, for goodness sake. Close for the width.
Mhm.
That's really weird.
Mhm. It looks like the other one we made.
Well, but I don't understand why this doesn't have any frame ticks. Oh, maybe we say frame arrow true. Okay. Okay, so this gets up to AX mul F. And then it's saying number of subsets of a set.
Wow, if this is right, it's kind of interesting.
Well, okay, so let's look here. Now, these are all claiming 44, 48, 45, et cetera, except for number of subsets of a set is 21. So this is saying, what's AX gen dot 1? AX1. So none of them depend on any of that extra stuff over on the right.
Right.
Let's find out what AX mul F is.
Wait, it does depend on AX mol F.
No, some of them
So-
do.
Some of them do, but once we get to hill X, we're done.
Multiplication of complex numbers.
That's mol F?
Yeah.
This deprecated axiom. Okay, what's this axiom here? AX rep. Axiom of replacement for Zermelo-Frankel set theory. Some things don't depend on it. And what's AX? Okay, but this is making the claim. Let me just understand what we actually did here. So this is saying that the out component depends on these axioms, right? And each one of these has a certain size of out component, right? But now a question is, how many times did it depend on each of these axioms in that out component?
Right.
How many paths were there to each axiom in the out component?
We could do this.
Actually,
exact-
even how far is it from this thing to the axiom in the out component?
we could reproduce this and then color according to depth, or basically the number
Yes.
of times that the axiom is used.
Exactly. Yes, we could do that. Exactly so. And we could also look at the distance to the axiom.
Yeah, we could do that too.
Right. So let's take.
But should
let's
we really include all of these axioms?
No, we should cut off these ones.
Yeah, we should cut that off. Okay, good.
It doesn't
Yeah,
care about those.
Yeah.
Okay, so then, and we should also, I mean, these axioms are nicely arranged into the set theory axioms. I don't know what these ones are. AX, AC, what are those?
I don't know. Is inf, what's inf? Is it or inf2?
What is, what is inf2?
Oh, that's an axiom of choice. AC, right?
It's not needed. Right?
Well, no, ANS int2. Axiom of infinity. Okay, so some things need the axiom of infinity, some do not.
But why inf2 and not inf?
Oh, God knows.
It's not,
Because
is
the
it
credit code.
arbitrary? Yeah, okay.
Okay, so inf2 is an AXCC. It's a real shame that Norm McGill died. It would be really nice to have him see all this stuff. Countable choice. CC is countable choice. I don't even know what that is. Okay. What is this one here? Axiom. Is that AX rep? Yes. Okay, so what we need to do here, let's just get the axioms which are actually used, because there's no point in including these ones. And then what we're going to do, let's just get axioms which were ever used, and then we'll have some things, and then we're going to basically make a depth map of how far is it or how many times was it used.
That's right. Yeah.
Okay, now the how many times was it used sort of one thing is the entailment depth to the axiom, remembering that we haven't gone through the definitions yet. We haven't expanded the macros. See what I'm saying?
Yes.
Yeah.
Okay, so first of all, let's pick out the axioms we actually care about. Okay, and so here, okay, keys of axiom assoc. So what we want to do is, this is axiom depths. Okay, so axiom depths, we say last/add axiom depths, and we say union of all of those. That's not what we want to say, union at all of those. Okay, that's the axioms that we ever care about, 49 of them. Okay, so now we want to sort those in the order that they appear in keys of axiom assoc. So how do we do that? We want to sort into the same order as this. So we just want to say, if member Q, keys of axiom assoc hash, otherwise nothing, and then we want to say that. No, I'm sorry, if member Q %443, and then we want to map that over keys of axiom assoc. Oh, for goodness sake. Did I get the member Q the right way around? If member Q, what's that?
Yeah. Second argument.
Oh,
So
it's because I typed it wrong, 433. There we go. Okay. So this is used axioms. Okay, so let's do the same thing we did here, but on used axioms. Oh, and what I also want to do is now, well, here, I just want to cut all these off by saying, let's see, they're length 29. So here, oh, position, I think we just say here 49, length of used axioms.
Okay. Yeah.
Okay, there we go.
Good. Cool. Nice.
Okay, so there are, it's going to be very nice because we can actually list here, we can name these axioms. There's just few enough that we can just name them.
Yeah.
So this here, E is transcendental, depends on CC, the countable whatever.
Countable choice.
Okay, so now let's take an example here of irrationality of the square root of 2 getting to AX13. So let's get the distances to all those things. Okay. So graph distance in Metamath graph We can also ask for shortest path. We can actually look at what the path is, what theorems it goes through, but that's a different issue. Okay, so Metamath graph distance there. By the way, where's the Pythagorean theorem?
Near the top. 1, 2, 3, 4.
Okay. What was its name?
Python.
Pythag. Okay, so let's just take Pythag to, let's say, AX8.
Okay. Nice. Okay.
All right. So
Great.
now what we're going to do is for each of these theorems here, we're
Yep.
going to compute the distance. Now, if I ask this thing to AXCC, it's probably just going to say infinity. Great, that's fine.
Cool.
So we'll just make this array of all of these things where they're either finite or infinity. Okay.
That's right. Yeah.
So then okay, so what we're going to do here is this is axiom depths, but we don't actually care about axiom depths. We're just going to use used axioms going straight from the original list of theorems, which was in famous. Right? So we would go from famous to, so what we're trying to do is, okay, used axioms is our list there. So what we want to do is for each element of used axioms, we want to go from, okay, so get distances. Oh, we don't even need to do that. Graph distance in here from the theorem to the axiom, used axioms, and then that from the theorem well, let's just say first of th goes to that last of th. And then this whole thing mapped over famous. Wasn't the most efficient way to do it. Well, this is too slow. Let's just check that it works on the first 3 of them. Oh, that's very wrong. That's what I want to say. Okay, that's our distances to the axioms.
Great.
Okay, let's do this. Let's do a parallel map of this.
Mhm.
It's a little annoying because we're going to have to send over that whole shebang. You know what? Maybe we should just generate the distance matrix. Forget this idea.
Where's the progress bar?
It's still sending data to the
It's not that big a job, is it?
yeah, because Metamath graph is a big object.
Wow.
If you ask just graph distance of the graph, would it produce a function?
Yeah, that was what I was going to do. I have a bad feeling about this.
Or distributing the graph across all machines.
I know, which is dumb. Annoying. I'm going to put used axioms up at the top. I think I have to kill it. Okay. Now here I only really need, oh no, I need set mm. Okay, so here I'm going to say okay. Okay. I don't think we need axiom depths there. So now what we want to do here is to say mmg distance equals graph distance of Metamath graph.
Maybe all.
Let's look it up. Is it graph distance matrix? Surely not. Oh,
It doesn't produce a function.
I thought it did. Isn't there a way to produce a function from this?
I think nearest does this, but not the graph distance.
Let's see what happens if we say otherwise we just have to run it. But I think these are, I mean, this will give us some sense here. I mean, I assume that this thing just This may be crazy to run the whole thing like this.
And we probably could have just run them all in pairs by now and have gotten all of them. Like it was easy to get 2. Could have just done that a couple of times.
I'm going to kill this. There we go. Okay, what I'm going to do here. I'm just going to say, just so we know what's going on. Actually, you know what? Why don't I go the whole thing? Okay. Here goes. Okay, so notice there was a 13 there. This will keep us entertained. So the basic depth, which is kind of interesting, is the depth is pretty standard.
10, 11, 12.
15, I saw there.
14. 10.
Is there another database in Metamath which is based on what's it called? On Piano arithmetic.
Yeah, there is one.
They seem to vary quite a bit. This is going to be quite colorful, I imagine.
$18. All right, what are we going to do in terms of color coding here? We want to basically go from from blue to red, going up to maximum values. So let's find out what the overall maximum that isn't infinity is.
Probably might be 18.
I don't know.
Wow.
But we can also, the actual graphs here,
Mhm.
each one has an actual graph. And this is the depth to those things. But now we have to ask how many times
Sure.
when we compile to that thing. Okay, so there's our result. Okay, so now let's say let's call this thing here famous depths. Okay, that's an amusing distribution. I mean, we can do the same thing from all theorems to their axioms, which I think will be worth doing.
Sure.
Although that will be dominated by ones that are fairly close. So for example, if we want to find the one furthest from the axioms, it's the antipode in some sense in the graph.
Hmm.
Okay, so let's get the max here. Oops. $22. Okay, who's the winner?
Okay.
position in famous depths 22, 36, famous depths 36. That's really weird. Okay, so 23 is used axioms of 23. And the axiom of infinity used in L'Hopital's rule.
Well, I don't think any of us saw that coming.
No.
Because of the derivatives, I guess.
Yeah, it's
Limit.
because of derivatives. Somewhere it's in the limits, derivatives. Okay, so let's now, okay, so we want a color map that is from 1 to 22, from let's say blue to red. Okay, so how do we do that? We say blend from, let's say, blue to red in with hash over 22 if hash triple equals infinity, then white, otherwise this. And then we want to do the same thing, this thing here, we want to take famous depths. Okay, here we go. It's just famous depths there. Famous depths. There's famous depths. Okay, then this wants to say color function arrow this. I'll say color function scaling. Arrow false. Let's see what that does.
Mm-hmm.
Ta-da!
Ooh, fun. Yeah, this is cool.
Okay, so then
So,
we should have a better color map.
yes, yes.
So maybe we want a rainbow color map.
Yes, I think so.
Okay, so how do we do that? We say color data of rainbow. That doesn't work. Let's see, 0.4. Okay, let's try this. Pretty space age somehow or something. This is such a weird business we're in, I have to say.
Ah, this is cool. I think
Okay.
Mario is going to be pretty excited to see that.
Yeah,
At
yeah, yeah.
least he should be. Yeah.
Now we have to figure out how to get rid of that frame. How do we get rid of the frame without getting rid of the frame ticks? Oh, I think we say plot range padding goes to 0.
Nice, 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 nice.
Good. So by the way, that means we should also add plot range padding to those
Yeah,
other
to several of these. Yes, I'll make a note of it.
Okay. All right. Let's just rename. Let's just so we understand. I mean, these we have to do a little bit of editing on the names of these theorems.
Yes.
It's really quite interesting, actually. This is sort of reverse mathematics. It's kind of a map of reverse mathematics. How deep?
Yes, yes. I mean, what's interesting is there are some axioms that overall demand greater depth than others, but it still varies amongst these different theorems.
Right. So let's go name the. Let's go make a map of what the axioms are actually called, and we're going to have to re-edit these, but we'll do that later. Okay. Let's at least do for the axioms. So we say used axioms, and now let's go figure out how to get. How do we get the names of these things? We can go. Let's do this. Let's just go.
They're all in the same place. Should be easy to parse.
You mean here at the very beginning sentence?
Description.
All right. So let's just okay. You think we can just scrape the descriptions?
Yeah.
By the way, Stephen, what's your position on including bar legends for this kind of thing?
In by bar.
Like it tells you, gives you a bar with the color gradient and then the depth number next to it.
We could do that. We'll worry about that later. Not sure how necessary it is. Except that I will. Okay, let's see what the legend would look like. I mean, let's see. What is it? Chart. There's a way of making a. How do you make that legend? There's an easy way to do that. Well, here, let's just do the following.
I thought it was just bar legend automatic, but that might not work for a grid.
Yeah. Let's do this.
My God, you made your own bar.
Yeah, except it's the wrong way around. There we go. Okay, so there it is. So I agree that that's useful to put in there. But that goes from one, and we could, if we really wanted to, we could just say frame ticks arrow true. And then we could say frame ticks arrow oops, that's not what I want to do. I don't know exactly how to do this, but no. Okay, well, frame ticks arrow true, none. Is it the other way around? None, comma, true? Why would it be the other way around? Well, whatever.
Okay, great. Now they know that that red isn't like 100 or something. Right. Mhm.
Okay, we can put in more numbers here. We should put in more numbers.
Well, my main concern was just if I'm a reader and I see some of those red squares, I think, okay, significantly higher than the others, but by how much? With this bar,
I
you
know,
get a
but I
sense.
think we can put in a few other numbers
Mhm. Well, okay.
because we should put the highest number in there as well. Okay, so use the axiom. So let's just import this as plain text. Is that what we want to do?
Yeah.
And then we look for description.
Yeah.
And we go up until what? The first period.
Maybe.
So let's say here, string cases of blank, 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 tilde, tilde, description, colon.
Punctuation character.
Say it again.
Punctuation character. I think you should stop at the first punctuation. Because sometimes it's a period, sometimes it's
I think we can
Oh.
overgenerate. Let's not worry about overgenerating, but well, okay, all right. You want to stop at punctuation character? Okay, we'll try that. I'm worried that the CC will be a punctuation character. Let's stop at a period. Should we do that? Let's stop at a period there, and let's have actually what we want here is shortest of x double blank tilde tilde arrow x. Okay. All right. So now here we want to go this here is, how do we insert this? We'll just do this as a, let's just do
string table. Backtick, backtick. Or just that.
okay. This might be worth doing in parallel.
Mhm.
Okay. Okay. So
Some of these are long.
I know, but we're going to shorten them. We got to write them
Manually?
Yes, we're going to do
Oh,
these
okay, that's
manually.
fine. Okay, cool.
But I don't know what axiom simp is. Maybe you guys could be looking these up.
Okay, if it is Simpson's axiom or something.
I don't know, but I think what we should do here.
Yeah, we can just start Googling these.
Well, no. Just look at the page. I'm saying we just look at the page. I think some of these just didn't have a long enough.
It's principle of simplification.
Ah, okay.
What is that? Is that a set theory axiom?
No, it's propositional calculus.
What the hell is it? I never heard of it. And it's not one of our notable theorems. That's the point. See what I'm
So
saying? Well, which axiom? Because what are the axioms of Boolean algebra that they're using?
No, just it's axiom number 1, so it must be important. One of the 3 axioms of propositional calculus. In Principia Mathematica called principle of simplification.
Okay, so it's an axiom. So this is an axiom of implication, right?
Yeah.
From implicational calculus. Okay, so let's go ahead and start typing these. Let me just start make a copy of this and just start. Actually, it'll copy down automatically. Okay. Let's just start editing here. Oh, Puffle. Not what I wanted. Help. Oh no.
I hate it when this happens. Oh,
That's all right. Modus ponens.
yes, right.
Let's put it here. Axiom of simplification.
Mhm.
Okay. Frege. AX2. Frege's axiom. Okay, transp. AX3.
Principle of transposition.
Axiom of transposition. Principle of transposition. Okay, what's this? AX gen.
Rule of
Generalization. But should we really say, well, I guess we could say rule. Hmm. Okay, yes, quantified implication.
Do we think that lowercasing is the right thing to do?
No,
Why not?
because the theorems are capitalized.
Well, I know, but we may lowercase those as well.
Really?
Or maybe we should just, let's leave these for now. Okay, all right. Let's leave these for now without capitalization distinctions, and let's just look through these.
Okay, okay. Okay, the axiom of distinctness, yes.
Okay, well, hold on. Axiom of quantified equality, axiom of extensionality, axiom of replacement, axiom of separation.
Well, oh, okay, yeah, these are all fine. I see what you did. Okay. What, ZF pairing?
What?
The long name. It's not very well named, that last one. This one's even worse. It has a comma in it.
Well, I'm not going to capitalize correctly. Okay. Complex numbers form a set.
This axiom is redundant.
Which one?
That complex numbers form set.
but it's still used.
Yeah. Not just, I think this particular one. Presumably.
No, I know, but if it's used here,
It just means human proved it using that axiom.
okay.
But he could have not used it and used something else.
Here, let's closure law. Closure law for real addition. Closure law for complex multiplication. Maybe we should just say closure for complex addition. Closure for real addition. Closure for complex multiplication. Closure for real multiplication.
Complex multiplication commutativity.
Commutativity of complex multiplication. I don't know if this should be capitalized or not. Okay. Associativity of complex addition. Distributivity for complex numbers. I'll have to do that a different way. It's interesting what some of these actually are.
Wait, that's too long.
Well, let's see how that works out.
Yeah. It's gonna be too long.
I know, but we'll just wait and see.
I guess so. Okay.
Okay. All right, so let's go ahead here and say axiom names equals #1 arrow first of #2 ampersand triple at this. Okay, so then we want to say, actually, we might as well just do this as an association. And again, we'll be putting this at the top. Let's copy this at the top. Okay, so now here we will say,
This is about to get some real hair.
okay, so now here we say axiom names, arrow brackets that.
It's not that bad.
It's not that bad. It's actually very nice.
It's not that bad.
And we could probably simplify it. Okay, so we could do a little bit of editing on this, but this is fundamentally a very nice thing.
Did you want to do another one for a number of times that the axiom is used?
Yes, we will do that, but I also want to what is this telling us? We're going to need to edit these names as well, but that's a minor thing. Where's axiom of choice?
It wasn't used.
Well, axiom of countable choice.
It is used
For Fourier
twice.
series and for E is transcendental. What is interesting is that the set theory axioms are pretty far down, pretty far away from. One thing we should probably do is what is the average depth of the use of one of these axioms in the famous theorems?
But we could do it. Yeah, we could do it that way too, right? Yeah.
Yeah, but see, we've also got the question of the. All right, let's figure that out. But I want to figure out where are we going with this. So well, let's just do the Pythagorean theorem and ask the question of the depth of things for the Pythagorean theorem, okay? Because it looks fairly typical.
Okay.
Okay. So its famous depth is 4. Okay. So now what we want to do here is actually for the Pythagorean theorem, let's list the axioms. Okay, so here what we want to do all right. We probably should put colors behind those things just to okay, not perfect, but close.
Yes.
Um,
Is there red around the infinity there?
something like that, yeah.
Okay. An error. Yeah, right. Okay. Okay, this is cool too.
Yeah, it is cool. This is a cool way of representing, you know, this is so we'll probably want to color code this to indicate we got a bunch of capitalization and things to deal with, but this is indicating. So for the Pythagorean theorem, okay, we could compare this to Euclid actually as well. How far, what are the, you know, with Euclid, it's kind of interesting to see how this compares to Euclid in terms of the depth here. Let's look at that for 1 second.
You know, there are two Pythagorean theorems in Metamath as well, right? There's Pythag, but then there's its twin. There's a second one, right?
Yeah,
I wonder if they differ.
I don't know, I'm sure they do. Okay, so we can also look at,
Because if you took the two of them, you could even take like their graph unit or something, and that would be that Pythagorean cloud
it is the Pythagorean cloud.
that you've been looking for. That,
This is a win. Let's look at the Pythagorean cloud.
yeah.
Yeah, that's a good point, because it's going to have a different characteristic from the axioms.
Mhm.
Okay, what's the other Pythagorean theorem?
Yeah, what's it called? Okay. Okay. Let's see.
I mean, even though these are in a sense just different proofs of the Pythagorean theorem.
That's the point.
No, it isn't. It's
Sorry?
actually that you can restate the Pythagorean theorem in terms of different axioms. And that's this compared to Euclid.
The other one's Python.
Pyth I.
Yeah.
Okay, so what we have is graph distance, Metamath graph, Pyth I, to hash. And now we have used axioms, right? Oh, it's not a valid vertex. It's not in that graph. It must be in something with piano axioms or something. Get what I'm saying?
Yeah. Yes.
Just the old graph.
I'm sorry, say it again.
It's the old graph, or not for the ZMM. Maybe
Which
for
old graph?
ZMM. The one you're using.
You mean I have the wrong graph?
I think so.
Oh, for God's sake. Okay, so let's derive the correct graph. How do we do that?
Metamath import should do it.
Okay, well, let's try it. Okay, so hold on. I'm still looping back on what we're learning from all of this. Okay, so one thing we could do we're asking the question, we're asking the question of okay, hold on. It's really interesting, but almost all of these theorems use almost all the axioms.
Yeah. And I wouldn't have guessed which ones do and which ones don't. Are there any ones here that aren't that surprising?
I don't know, the fact that it takes so much effort to some of these to get. Okay, so let's also look at okay, so anyway, the conclusion this is all relevant. Okay. Okay, how do we use the definitions? What are the definitions telling us here? The definitions, we're going down to a definition. And then from a definition, that's basically extending the graph, is it not? As we get down to, if we get to definitions, the definition is not the end of the story.
No, the eames are the end of the story.
Right, but the definition, these are direct accesses, right? These are direct accesses to the base, as opposed to through definitions. So we can
Okay.
also ask, how far does it take to get to definitions?
Yes.
right?
We can ask how many times the axioms are used. And we can also do the same thing now with definitions. Same thing.
Right.
So we have maybe three others of these we can make.
Well, we can do
wanted
that
to.
for definitions, but the definitions themselves will use other axioms.
I don't think the definitions use axioms.
What are the definitions in terms of?
Just
All right,
W.
let's look at definitions.
Didn't some definitions still have hyperlinks? But they had eames. But didn't they also? I don't know. Not sure. We should check.
Okay, so how do we get the definitions? Def a soc, I think, was the definitions association. Oh, here we go. Def a soc there. That's an awful lot. Okay, so then we can ask the question, which of these definitions has the largest in component? Right, so we can ask for each of these in the Metamath graph, length of vertex in component Metamath graph hash, let me say hash arrow this, that's just keys of that, right? Okay. All right, so now let's say sort by okay. Maybe we already did this. We already had, let's see, we said log oops, why doesn't that work? Okay. So that's the number of times each definition is used. So, unlike DFBI, what's the role of these definitions again? What does DFBI actually say?
Introduces a new constant. It extends W of X.
Okay, but so what's the role of that in our, again, the definition is just notational. Is that right?
Wow. guess so. Yeah.
So
I
a
don't
question.
understand. I mean, DFBI, it has hyperlinks in it, you know. Like it has eames. It has this psi eam and this phi eam. And then it has these what's all this other stuff? What are these other hyperlinks? What's this
Define
WB?
biconditional.
Like what?
That's just a breakdown of its syntax.
No. Like these hyperlinks and these references. What are these? What's all this stuff?
Syntax
Just a
references.
So what does that mean for our purposes? Are these also just eames, but they just have their own links?
Thinking. So in the case of Boolean algebra, we can state theorems in terms of NAND, or we can state the theorems in terms of ANDs and ORs.
Mhm.
And um, let me
Yeah.
no, I'm thinking. Sorry, I got distracted by a random piece of mail. I'm thinking. So what does it mean? We're saying we define these operators. Yeah, I mean, this is just different emic projection, so to speak. Different operators are just different. It's different coordination of the Roolead, basically. You know, that's really all it comes down to. But different operators, let me make a note of that point.
What does that mean? Basically, everything on that definition page, we could build that out of combinators or some simple rule, basically.
Yeah.
Yeah.
So in different, look, what we're saying here is different definitions are different coordinatizations of the Roolead.
And then we build entailment cones from those coordinates, basically, and fabrics and so on, right?
Yes, but the coordinations of the Roolead, i.e. different observer frames. In other words, i.e. an observer can talk about logic in terms of and or, implication, etc., implication not, you know, NAND, etc.
This is it.
Yeah.
This is it. This is where the reference frame begins. It
Yes.
begins with with
what you're talking.
plucking these out of the EAM level.
Yes.
Yes.
Right. And you can
Yeah.
choose to.
Yeah. Yeah. Oh yeah, sorry. Go ahead.
No, no,
You
no.
can
I mean,
choose to, yeah.
no, I'm thinking. I mean, right. So this is notation that you're using to coordinatize, and you could as well state logic. When you state logic symbolically, it's a little confusing because logic has this models thing where you can, what's the relationship between models and all of this? Models are another coordinatization mechanism. That's an irrelevant point. I mean, you can make models of and or and so on. That's an irrelevant point. This is the coordinatization. Okay, so these are coordinates, and then that's what the definitions are doing. Then we've got axioms. That again are another kind of coordinatization. Right. So here, okay, so we can state a given theorem can be stated in terms of these different operators. So for example, let's say we say P P and Q or R. Okay, and we say Boolean convert I wish this was scrapable. God, so stupid. Typical example of a table that should be scrapable. Okay, let's take just those. Okay, so each of those is a different representation. See what I'm saying? The exact same, I mean, we can state it, we can actually have a theorem about this, but it's a different representation of that theorem.
Okay. Yes. Okay.
So that's the way to think about. That's a recoordinatization. Then, for each theorem, there's a different proof path depending on what axioms we use.
Wait, actually, what we just did, are those really theorems or are they just
No, they're just
expressions?
I didn't make a proper theorem.
Well, should we, or should we just call it an expression?
We'll deal with that later. This is going to come out. It's okay. We'll pick a nice theorem, and we'll write both sides of that theorem in terms of NAND or something.
You make a comment.
Yeah, I will. But I mean, I know this. Okay.
Well, it's a big post, and there's a lot of content.
Okay. All right. Yeah, this is nice. This flows well. Okay. It's just very unclear what this is. This is
Wait. Let's not interrupt ourselves. We can get back to this later. We were doing something specific.
Okay. All right. Okay. So this is a coordinatization. We also had, remember where we talked about axiom systems in the wild? Down here, you see we've got these multiple Boolean algebra axioms.
Yes.
Okay. So what we do with those, there's a lot of really nice stuff here.
And much of it's been produced within like the last week and a half, really.
Well, a bunch of new stuff has been. Okay. Okay, let me just make yet another one of these, okay? I want to do a Boolean. Actually, hold on. Nick, I just want to get all the axiom systems equivalent to Boolean algebra.
Okay.
Just from axiomatic theory. You just get one thing to eat. I'll be right back.
We already had those, right? Remember the graph. It's already in our working material.
Hi there. Okay, did you find things
We
equivalent
already did
to?
that.
Sorry?
We already did that. If you open the Metamathematics 76,
Yeah.
just take this data set. You can extract it easily.
Okay.
Nick, is your neighbor doing it again?
Yeah.
Oh my God. That guy.
Okay. Equivalent theories. Is that what we want? Well, there's Boolean axioms. Okay, we just.
Yeah.
What the hell is that structure? Okay. And Boolean axioms. Okay, so those are all the axioms. Actually, what we have to do is translate a theorem so a good theorem might be not of not. Okay. What's your favorite theorem? The favorite theorem might be, let's do not. Not of not is so that this is okay, that theorem there. Is that a reasonable one? So in terms of these different things, we have Boolean axioms here. So for each one of these, we want to say axiomatic theory of hash, comma, do we call it operators? Okay. So many of them, it's just overbar of overbar. Except for the NAND ones. What is not in terms of NAND? I know I have a table of this in the NCAS book. Here's the table. NAND. Oh gosh, which number is not? Not is 3 or 5. 5. Oh yeah, it's just NAND of thing. Okay, so it's otherwise known as NAND of thing. So that's not. So not of not is nest of this, comma p, comma 2. It's that. So the theorem is either overbar so you get what I'm trying to do here. I'm trying to say, actually we state the theorem. We're going to do a find equational proof. Oh, I'm going to do pure hackalola here. We're going to say if length equals 1, then it's going to be this thing slash dot and arrow center dot. Okay, otherwise it's going to be overbar of overbar p equals p equals p comma. Now we go hash. Let's find equational proof. Let's say proof. Well, let's just do that to begin with. Oh, what the hell? Just do this. Say hash goes to this slash at BAX. You can't prove this, right, in all of these cases, surely. All right, so most of them look quite easy.
What if there are two operators? Like for or an and.
Doesn't matter because we know I have that. There are no or an and. It's always got not. So we want to make a table here. That shows that's interesting. I wonder which one is the slow one. We could have an echo, I suppose. Then what we want to do is we want to make a table where it's the theorem with its operators. Well, no, the axiom that's being used, the theorem with the operators, and probably the length. I mean, maybe what we'll do is make pictures. It's probably more dramatic if we make pictures of the proof graph.
Okay.
kind of dramatic that it can't prove this.
It hasn't proved it.
Old Kurt is rolling over. Oh, Kurt's just like, I told you so.
Well, she's probably saying, how can you be eating? Aren't you worried that it's poisoned?
You know, as I understand more about Gödel's view of mathematics and science and so on, all this stuff about not believing in doctors and such like begins to be. I mean, this quote from a person on your institute who'd met Gödel, he just joined there, who said, "Young man, I don't believe in natural science."
Yes, yes, right.
Well, we can leave this running another time. Let's go ahead
let's
and
continue.
let's go ahead and just limit these by if something is interruptible. Nope, nice, it aborted. Okay, let's just go ahead.
I think it's Robinson axiom. For some reason.
Robbins. It's unexpected. Well, remind me before we wrap up to leave it running overnight. You were right. Well, that's kind of interesting. Okay. So we want to make this table that gives it's really quite cool, actually. Now, these are bizarrely in alphabetical order, so that is not kind of how we would like it, but let's just do this. Let's get rid of Robbins. Put or not. Okay. And now let's go ahead and say, okay, so we're going to make, oh gosh, we don't have, do we have the actual names? Well, here, let's just do that for now. Let's just say, the axiom, so we want to say, first of, well, let's just do #1. The theorem is Okay, we're probably going to want to state these axioms differently. And then we're going to want to say of the axiom, axiomatic theory. How do we prune off all the cruft from axiomatic theory? You know what I'm saying? That
What
all the for alls and all that kind of stuff.
no, for alls is just you just take last of each for all, I think. Don't have to do anything.
Okay, and what about the unformalized symbols?
Yeah, and that too.
Is it proof length, right? And then the last thing we want to do is rotate of proof graph. Oh shoot, I need to run the code 01, which I haven't run here. Of #2, and then I want to say rotate that 90 degrees. I don't know whether that's going to be the correct 90 degrees, but we'll worry about that in a moment. And then let's say grid. Oh shoot, that's not the right thing. I want to do triple at there. Oh, how do I get the how do I remove the labels?
What
Do I
was
say these ones? Yeah.
vertex shape function? Post static. I think I added options to the proof object token graph.
Okay.
Right.
That's cute. Okay, so let's say how do we get rid of that hypothesis thing? We just say here, vertex labels, arrow blank, arrow none. And then we say image size goes to, I would say, say 100 here. And then let's say here, the Sheffer axioms there. Okay, so we want to say here slash dot center dot arrow small circle. That's all we need for that. And then here we want to say slash dot circle times goes to, well, let's for now say wedge, circle plus goes to V, overbar is fine, center dot, goes to small circle. That whole thing is traditional formed. How could that be that big when I told it 100? So let's say 100 comma automatic. And then let's say text of this whole thing. That's rather swank, actually. I mean, there's some glitches here, but you get the main point, right?
Yeah, they're cool. They look. I prefer them when they're horizontal.
Yeah, well. Okay, so then. So what this is showing is, I think these should be much smaller. So I'm going to make these like.
The only other comment is these two shades of green, like they're too close.
Oh,
I
yeah,
think.
yeah. I know. We still have to work on all that stuff. Okay.
I don't think it just hasn't been mentioned before, so I had to mention
Okay.
it.
So this is the thing.
You want to get rid of those brackets?
Which brackets? Oh, the braces there.
Yeah, sorry, the braces.
Well, we can't easily do that because we have to do, I suppose we could riffle some kind of vertical bar here. If we're going to do that, what we have to do here.
The other thing is,
Hold on.
yeah, okay.
We'll riffle some kind of thing here.
The other thing is, you have what is it? You have You have two expressions on this in this first column. If you indented, it would take up less room, and you could actually probably see the pictures more clearly, right?
Expressions where?
No, like for the first row, right? For the Boolean axioms row, right? We have one. Actually, we have three. We have this expression, comma, this expression, comma. Oh no, we have four.
But we could probably
Five.
stack these
Yeah,
expressions.
we could stack.
So,
Yeah, right. If you stack them,
right,
then
okay,
you're gonna have more room for the pictures.
Yeah, all right, okay. Oops, that's not what I want to do. What am I doing there? Do that like that. I want to say column. Okay, so there's some goofballery here, but we'll worry about that later.
Yeah. Okay.
That looks nice. Okay, so we have to probably move these around a little bit. Actually, let me just rearrange these a little bit in order. Now I want to put hunting glue for or not. That's really weird that these alternate axioms down here prove things in a vastly different amount of time. That's a very nice, interesting thing here. So let me just
Yeah. Well, the Wolfram ones certainly stand out, don't they?
yeah, but
Oh,
these
well,
two,
that and the that and or not.
honestly, this here, I think what we should do is just forget the name. Okay, so these are different axioms. This is really a nice thing. This is really a nice thing. Different axiom systems proving these things in different amounts of time.
Yeah.
Now, we could also imagine okay, let me just put this in somewhere. And I might try and run that Huntington axiom thing over.
But should we make that apocryphal Pythagorean cloud?
Yeah, hold on 1 second.
Yeah.
Yeah, we should do one minor thing here. Isn't there a divider style?
I'm not sure. Nick, is there a divider style?
Again,
Okay, that's not quite
divider.
right. But that's
Is
not
there
quite
a-
right, but it looks a bit better. Okay. So back to this, we are looking at what we've established here. Okay, so this is the Boolean axioms, and this is saying, so here we need to have different representations. Let's see, in terms of different operators. So we want the given truth table, right? Yeah, that's all we're doing is, so if we say it could be equivalence, okay, so what we're saying is, let's say it's Boolean table of P and Q or R, PQR. Okay, now what we're saying is, we want to express that function
Okay.
in terms of other operators. So for example, if we say and not, let's say. So we say and arrow 2, not arrow 1. Well, actually, I hope we won't have too much auto-simplification, but groupings of we want just PQR. So let's just try PQR of this. And then for each of those, okay, we want to say Boolean table hash comma PQR. Well, we want to say select okay. So then, for example, we might say the same thing with NAND. Okay, didn't work. So then what we have to do then is we want to do PQR, let's say PQR. That's interesting. So, well, let's see. Oh, that's in this particular order. So we want to take, actually, we want this to be mapped over tuples. Look, it's this thing. Mapped over tuples. PQR, comma, let's say 3. And then it's the catenate of that. Okay. So those are those. So now if we say or not, for example, okay, that's dandy. So now if we say NAND, let's just say NAND arrow 2. Well, actually, these might work for a lower tuple count. So that was tuples of, oh no, 3 means that's the minimum we could possibly make it work for. Let's do NAND and not. Okay, fine. So there are lots of those. So let's now say just NAND on its own. Okay, didn't work in that case. Okay, so let's go up to 4. There we got it.
Nice.
Kaboom. Okay. What other things? We could also have implies.
Okay.
I mean, there's a whole bunch. I listed them in chaos. Here we
Yeah,
go.
yeah. XOR XNOR. Is that an
Yeah, we could
option?
do that, but we could do that. But I think what we want to do here. Okay, so what we're doing here is we're saying, imagine we are trying to represent and this we would do with and or. Which we could also write as or of and PQ, comma R. So let's see, for maybe we want something. No, that's okay. We can, this is okay. Let's use this. And so then what we want how do we write something which says, okay, so what we want is the first of this. Okay. How do we do this? We say while, how do we return something where we want this thing to increment until, do you get what I'm saying?
Nest while.
Actually, maybe what I want to do is just say table of n comma 5, 6, let's say 5. If hash is not equal to nothing, then throw hash. Otherwise hash, this is really ugly. Let me say catch that. Actually, we could just do a do here. Okay, then we do first of this. Okay. And now we do that over ops. Okay. And let's do parallel map over. And now we want to do and or not. It's the first one. We're going to do and not. Do or not. We do implies not. We do XOR implies. We do, oh wow, operators 2 and 13 I had before. We do NAND. And we do nor. Let's do NAND, and I'd have thought XOR and not was worth doing as well. Okay, let's go try and do this. Oh. Mistake there. Did we make a mistake? Is something not functionally complete? That looks unpromising. Just go up to 4 here. Is there something in this list that's not functionally complete? First of null implies XOR. Oh, well, maybe XOR not isn't functionally complete. I actually didn't know whether it was or wasn't. Okay, so let's go ahead and say, oops. So let's do this of first slash at ops, comma, this whole thing, grid, from arrow all. Wait a minute, why is that so complicated, and or not? Oh, I need to do first, I need to do a sort by here. Okay, that's kind of cool. So that's showing how those different operators manage to construct those same expressions.
Right.
And arguably, hold on.
Yeah. This is helpful too.
No.
It's like an expression cloud.
Yeah,
Different kinds of clouds.
right.
Right.
This one, actually, the way I should do this is, that's the correct version of this. Okay, but I also want to try when this is XOR P XOR Q and R. Really? Why is it saying that? Why is it saying null? Well, I think we should do the XOR case because this is a case where things will get considerably more complicated. Really? Why is it saying that? Do you understand this?
No.
Well, I don't know.
Oh,
I see. The problem here is that this probably needs to go up to 5. Why does it say that quickly?
Well, just one operator. There's much less groupings.
What do you mean? What?
Well, for NAND and NOR, there's much less groupings, right?
there's just a
Overall
single operator.
feature.
Yes. Yes, but why does this say? Well, here, let's just do this with map and then we can do a backtrace.
Well, it just didn't throw anything. So it's a null. I guess catch returns null.
Yeah, I understand. But I just wonder why it can find. Oh, you think it's finding it quickly, but just because that. Okay, well, let's go up to 7 here. That's kind of nice.
Well done.
That's kind of nice because it just illustrates that it can get kind of complicated.
Yeah.
I'll put those next to each other probably. Oh, we
Oh.
need different notation and so on.
Now we still had those other the grids for the theorems. We wanted to do one that color coded it according to the number of times the axioms were used.
Yes, I know. So let's just figure out how to do that, and then it's wrapped.
But what about the Pythagorean cloud?
Oh yeah, yeah. Well, how do we do that? Because we've only found one Pythagorean theorem. Oh, but we want to just do it with the different fundamental axioms. Because we've got one from set theory and we got another from something completely different, right?
But do you think there'll be any overlap?
No.
The axioms?
No, but that's okay because it's fishing different things out of the eames.
Okay.
So I'm saying different
what would
axioms.
but what would it look like visually? Would it just be two completely different graphs?
Yeah.
Well.
Yeah, but I mean, I think.
Why? There's still intersection.
Is there?
There
Even
should
if
be.
theorems, well, I don't know because these different set.mm and set. Something else.
No, I mean like those two Pythagoras theorems is just in set MM.
Oh, they are? Well,
Yeah.
it wasn't found in set MM the last time I looked. Here we go. So look.
No, it's just because you have an incomplete graph. I already told you.
Okay.
It's either generated for I set mm, or I don't know, pruned somehow. I'm not sure.
Okay, so we need the complete thing. So we need to get,
Yeah, complete graph is like 95,000 vertices.
whereas this is 35,000.
Yeah.
Okay, how do we get that? Do you have
Just
it?
use Metamath import. I don't know how long it would take, but
Okay, well, so Metamath import of,
just use an example.
so say it again?
Just use an example. I think I have one there that returns a graph.
Proof graph, okay. But so how do I
Check the neat examples. I think I have for I set mm. You just need to change one letter, like this one. This took me 43 seconds. Well, it's with verification. I think it can be disabled.
okay. So then we're going to have to recompute everything using this graph, which we will save. If we can get this graph, we'll save it out to the,
Yeah.
okay, then what we want to do is pith G
It's
versus pith.
Pythag versus Pith I. Pith. Yeah.
Okay, but the thing we also want to look at, do they also have the Peano axiom somewhere? And what is I set MM? What's the difference in I set and set?
I think it's without axiom of choice, like into initial. You get it.
Isn't there a piano.mm?
Yeah. There's also piano.mm.
Does that bother you? What's saying there? Oh, we got back. Okay, so let's go ahead and save this.
Check whether it's correct, because I don't like those errors.
Well, should we see where these came from?
Maybe just vertex labels or graph.
Vertex list, you mean? Well, let's do vertex count.
Oh, yeah.
That's a big graph.
Yeah.
Okay, well, let's just get a sense of, I mean, let's just see whether our previous calculation of the things without that have zero vertex out component, right? That should be the axioms that have zero vertex out component. Is that true? No, we want to select in vertex list a full set string starts q ax dash. Okay, let's see how many of these there are. I think this is very comparable to what we had before. So let's say used axioms, and let's say length of that 49, let's say take from 214. They're not the same.
It's not just take, right? We selected only those that used by those theorems.
You're right. You're right. So let's see. So how do we, used by those particular theorems?
Right.
Right. So what we really want to do here we could do this same thing again here, but with the new graph. Actually, let's look at the Pythagorean theorem in the new graph. Oh no, famous depths was computed separately. Where was famous depths computed? That was computed here. Oh, let's just go ahead and do it.
Do you want to use a different list of axioms there?
Why?
Because they're different.
Okay, how do I find out what they are?
We just repeat what you've done before. And probably this graph should contain more theorems of the list, of the original 100 list.
I know. Shoot. Okay, look, we're going to do that. Let's just look at the roadmap of what we're going to do. Okay, because then we should start thinking about, okay, so because we know roughly what's going to happen here. We're going to have two Pythagorean theorems, which are essentially the same theorem, we think. Or do we not think they're the same theorem? They have different proofs. So we probably don't even know if they're the same theorem.
I think another one is just a generalization to different spaces.
Yeah.
High dimension.
Okay, well, fine. So there's only one known example of this. Okay, so again, let's look at the map here of what we're doing. Okay, because we can obviously we need to redo this for this full graph. Let's also look at, do we have the Peano axioms here?
Or do you need piano.mm?
We need piano.mm, presumably.
Okay.
The same link.
What would it be? Piano.mm master. Is that what it is?
Oh, only the last one. The first one is just ZMM.
That didn't take very long. Okay, so let's say well, that wasn't good. Is this really right?
Yeah, I'm checking. blob.
That's there. That's a README file.
No, it's a database.
It's not. I just went
It's just
to that.
a bunch of comments and definitions. See, there are some definitions there.
But this just imported nothing. Well, let's see.
Try without a graph.
Okay.
It's weird. One more bracket. And now graph again.
Of this or what?
No, just again like comma graph. Proof graph. Weird.
Maybe there's some simple bug
Maybe
here.
there's no, I think there's no theorems, right? It's just a list of axioms. It's just a database without theorems.
Okay, so do they have theorems of pure arithmetic or not?
I don't see any theorems, just axiom there.
Okay, all right, so there's nothing here really.
Yeah.
Okay. So, I mean, this is probably not interesting. Okay, so I mean, there's some cleaning up here of, okay, so the one thing that we did want to do, which we'll do, we need to clean up how the full set of mem works. But let's just do one effort here with the original.
Mhm.
Do we care about doing? Oh, I see. That's all possible depths there. So I just wonder what the depths. If we start from every node and we try to get to the axioms from every node, right? What is that computation? You see what I'm saying? We look at every node and we ask.
Do you want the histogram for it?
Graph
No, that's
distance.
what I'm. What's
Yeah,
that?
why not?
Yeah, we want the graph distance from every node to a particular axiom. So let's say, I don't know, the first axiom in this list. No, let's not do the first axiom. Let's do to which axiom?
One that's commonly used and that's not too deep.
Okay, how about the axiom of existence?
Nice.
Okay, so which one is that? That is axiom of existence, AX6. Okay, so now we want to say distance from all nodes to a particular axiom. And then we could look for each axiom, we could make a histogram. Okay, so then AX6. So we want to say Metamath graph. So what's the way to do this? This is, we could reverse the graph. No, it doesn't really matter. We just want to say graph distance, if I'm not mistaken, of that hash, comma, AX. What was it? AX6.
You want a different graph? It's the old one.
This is the old graph. I know because I'm not going to do it on the new
Okay.
graph yet, because we're going to need to do the new graph soon, but we're not doing the new graph yet. There's no faster way to do this, is there?
Maybe you just can provide a list for the graph list.
Oh, let's try that. Well, let's just see. No, it doesn't like that.
Yeah.
Well, let's do something outrageous. Let's just say random sample.
Maybe we should have been. Oh,
Okay. So from a given axiom, we'll have a distribution for each axiom. It'll say how deep that axiom was from a given
yep.
thing. Now, I don't know why we care about that. What does that mean?
I'm not sure exactly what it tells us. Besides, I mean, what besides the obvious?
Which is what?
Well, that it says something about the relationship between the axioms and the theorems and how long it takes to reach the axiom. I mean, but just besides what it measures, I don't know what the meaning is of what it measures.
Well, it's basically how far you have to go in this dependency entailment cone
Yes.
to get from, so certain theorems, I mean, certain theorems are different distances for different axioms. So it's kind of like hard to know.
Yeah, right.
It's kind of there's a certain, well, there is a question, which is for every theorem,
Mhm.
what is the deepest you have to go? For any axiom you're actually going to get to, what's the deepest you have to go? So that's the thing we could work out for way up here. Note could also figure out the deepest one has to go to reach an axiom. See what I'm saying?
Yeah. A lot of loose ends for this section still.
I think it'll get less loose when we actually start writing. I think the only question is, I just have to remember what these subsequent sections actually say. Okay, we've also got these things here, which are distribution of sizes of proof graphs for theorems in different areas. Not sure how relevant that is. Yeah, this is going to be okay. Those two sections are not those two sections will not be seriously affected by what we have to say here. So the only okay, so we've got a Pythagorean version. All right, so in Euclid, this is theorems of Euclid hanging below their axioms. Okay, and in Metamath, we're going to have the same basic thing, except that it's a much bigger graph. Does that make sense?
Yes. It must be. Yeah. Right.
Okay, so the fact is, what does it mean? It is really kind of interesting that things depend on, most of these theorems we care about depend on all the axioms. That's the knitting together of space, basically. That's the knitting together of mathematical space.
Yes, right. They're kind of clustered together in mathematical space.
Yeah, I still don't understand the interpretation of that picture there. Okay, so hold on a second. Well, look, the general thing we're seeing here is that mathematical space is well knitted together. But we can form a branch shield graph.
No, it's our reference frame is well knitted together, per your point before, right?
What do you mean?
You made the point
Oh,
before
I see. It's coordinatized, right? In our reference frame.
Yeah, our reference frame is well knitted together, as it should be. Otherwise, it would be really difficult to do mathematics.
In our reference frame, things are well knitted together.
Or even the way we've populated metamathematical space, those populations, so to speak, are well knitted together.
Yeah, right. Our population centers, our populated places. You see, this is the problem. I work on enough different things. They're called populated places in geodatabases.
Yeah.
Our populated places are well connected.
Even though well connected means something else too.
Yeah. Okay, but anyway, so then that's what this means, is that it isn't the case that there are very separated I mean, in the branch shield graphs for this, there's all kinds of questions about entailment fabrics for these and so on. Okay, but I think what we want to do.
Yeah, go ahead.
I think the main point here is, what are the main points? The main points, we want to get to that picture there, which is the we could do the same thing for Euclid. How far But this has a lot more axioms. That's the point. Ugh. Whatever. We'll figure
That
it
was
out.
nice. Yeah.
We'll figure it out.
So in terms of schedule, let's see. It seems like you have quite a bit of writing to do.
I have
Of
a lot of
course,
reading to do.
of course, we can attend those sessions. There's still this question of monotonicity in models, and then there's the
I want to concentrate on
Gra-
this until it's done.
no, I know, but I'm just addressing what else has to be done. That gravitation section, and then we count the eames and we do the Scion comment. Okay,
Yeah,
this might take another full day, this empirical metamath section.
it will for me. Yeah.
Yeah.
Not to mention. I think we should mention that we use Metamath, and Norm McGill recently died. Don't you think that's appropriate to mention?
Yes, yes. I mean, Mario was also willing to meet with us. Might want to thank him.
Oh, I think I did.
Okay.
Yeah.
Oh yeah, there he is. Great.
There's a whole bunch of other people I need to put in there, but that's a different issue. The super axioms. Okay. Oh, that was the one thing we were leaving out, is how many times does a given axiom get? This was really hard to compute for Euclid. Maybe Nick has a clever idea about how to do it, but I don't know how to do this. I mean, in other words, you are going from a theorem. What does it even mean? It's all paths to reach that axiom, right? That's what you're trying to compute.
Wait again, the super axioms, what is it? It's
No. I'm asking, we want to compute. There must be a way to do that by weighting the graph. Okay, we want to know how many different paths are there to reach a given axiom?
a number of paths.
Right. So the Pythagorean theorem here, how many copies of each axiom are there in the Pythagorean theorem? See what I'm asking?
Wait, not really.
Okay, so we go through, we're trying to find that theorem, okay? Eventually, it's going to visit all the axioms. That's what we see here, right? It has certain depths to visit all the axioms. The question is, how many, if we look at all the possible paths, how many different
axioms?
How many paths? Yeah, no, we look at all the paths to reach, let's say, the axiom of distinctness. I think this is what we're asking. How many such paths are there?
From the theorem to the axiom.
Yes, because that's the number. If we compiled the theorem down to axioms, that's the number of copies of that axiom that would appear in the compiled statement.
Yeah. I don't know. I don't know how to efficiently count all possible paths.
Well, when I did that for the Euclid thing, it was really hard.
You didn't use any fancy algorithm, right? You just
I think it was slightly
find.
fancy. There it is. There's the Euclid case. Lengths of the axiom sequences for all theorems. The final sequence of axioms has length 835,000. Okay, so there, suspect that. How the hell did we work that out? Was that I think we accumulated. You understand, as you get to every node in the graph, right? You can work upwards from the axioms.
Yeah.
And every node accumulates.
That makes sense. Just count the number of axioms or edges, whatever.
What does that mean? Count the number of edges to what? To
Each of them, well, given a graph, right? You just start from the axiom, follow its what that would be its ancestor, right? And just increase your counter for this axiom, for this ancestor. Now you have all the countings for in this node. Then you just go one ancestry up.
okay, so hold on. Vertex out component of Metamath graph, comma, Pythag, right? That will give us the Pythagorean graph. It has 7,000 nodes. What is that? Oh, vertex out component.
Yeah.
Okay, so now the nodes at the end, we want to count. So for example, counting the number of paths. How the hell do we do this? Count the number of paths to I think what we do is we accumulate up from the leaves here. Yes, this is what we do. At every, let's look at something very close to one of those leaves, okay? Then what we do is we say, as we accumulate up from the leaves, we keep the set that is, as we go up from the leaves, each node has a count of the number of ways it's reached. You see what I'm saying?
Okay.
That's kind of what I was describing.
Okay, so how do we actually do that? We do we reverse the graph. No, what do we do?
No, we just first you create like an association for each vertex, empty association. Then you can create some recursive function that just
I think this
populates all the counts.
This is a Nick programming special. I mean, I could do it too, but you'll do it very well. I think this is okay. So the goal is to basically be able to compute something like this, where we can basically say for each axiom, how many times was that axiom used in the compiled version of the Pythagorean theorem?
Okay.
Fine.
Okay, so this is a to-do. I need to go to sleep. there are so many, master's theses, PhD theses, etc., to be written about empirical mathematics. It's kind of shocking that there are so far zero, so far as I know.
I'm not that shocked. I'm not that shocked, but with these as precedents, the number of excuses for not doing it are
Yeah, but I mean, look at
smaller.
the
The
Euclid.
only excuse is my advisor has no idea what I'm talking about.
Yeah, but it's just like it's like with rheology. There's just so much grist for people to do interesting work.
Yes, yes, but I think that we'll have to provide much of the infrastructure for that grist.
Yeah, maybe. I mean, maybe big lists of. I mean, look, the big list of unopen questions from the NKS book. You know the story, right?
I've read that piece. I think Jonathan's read that piece. Maybe Nick's read that piece. Nick, if you read that open questions on, if you read that, it's some old article that Stephen wrote.
Well, I never finished it. I only got to about chapter 3. I mean, and arguably, I should finish that for the 20th anniversary. That would be an amusing thing to do.
But there's also, what is it? Hold on. There's also, what am I looking for? I'm looking for. Wow, maybe I'll find it later.
Okay. Anyway, all right, sounds good. Well,
all right. Well, we're getting closer. I mean, I know I feel like I say that every day, but
we are getting closer. I mean, it's just the only thing that happens is every time. I mean, data, unfortunately, has a habit of telling its own story. And
yeah, I know. But I do fear that this project is so rich and there are so many rabbit holes. You can just keep going and going. What about this? What about this? What about this? What about this?
I know.
At some point,
well, we're getting close.
We'll have to cap it. Yeah.
Yeah, we are. This is the last hurrah. Okay. Then,
you say that. You say that. We still have to do the gravitation section.
I think we may cauterize much of the gravitation. The pieces we haven't done, we may not be able to figure out. And
yeah, okay.
Okay.
Yeah, with that cauterized, then we
that cauterized, we're basically done.
We just count there's this model theory question of monotonicity, but if we can address that, in less than 2 hours, then
I think that one is either pretty obvious or we're going to have to say we don't know.
Great. And then we count the eames.
Yes, which may or may not work out. And then we're into kind of cleanup.
Yeah, yeah.
Ehor. Okay. That's all right.
Right. Well, so wait, what's the schedule for tomorrow, by the way?
Let me look.